can't share my screen.
Oh, okay.
You have to permit me to do that.
Can you do it now?
Let's see. Share screen. Mozilla Firefox. Share.
Boom.
Yeah. I had to remind myself if there's a hyphen field effect. There it is. All right, so I guess this is what I wanted to cover. So we'll start with the DC response of resistors, inductors, and capacitors. So I'm hoping most of you know sort of the basics of each of these components. Maybe not inductors, they're a little bit more advanced, but we have resistor, capacitor, an inductor. Oh, that is a diode. Why? Oh. All right, L is now a diode. Draw passive components, add inductor. Okay. All right. So, basic thing about resistors is if you have a DC voltage, so any one of these things, we can go voltage source. Of course, this is a two-terminal voltage source, so the positive is going to be the larger side and the minus will be the smaller side. And we'll start with 10 volts. So if I'm guessing you've all done Ohm's law, so you'll know, why is this doing diodes? You'll know that with 10 volts and 1K, you should expect 10 milliamps. You can see that down in the bottom right. So what you'll hopefully gain over doing lots of things like this, be able to like quickly do Ohm's law in your head is the good one. So 10 volts, 10K, 1 milliamp. And you'll know that a resistor is in series will add their resistance. So the combined resistance here is now 20K. That's 10. So let's see if I can do this again. Oh, you can't draw in here. All right, that's too bad. So resistors in series add their resistance. Resistors in parallel are going to essentially divide their resistance. So if you have two 10K resistors in parallel, you'll end up with 5K. Let me see if I can pull it here. Can you just see my browser?
Yeah, we can just see the browser.
Let me see if I can change this. Stop sharing. New share. Entire screen. Share. All right.
I sent it in the chat, but just to make sure you guys all know, feel free to interrupt at any time.
Yeah, please. If
ask questions. Slow, if you're like, I already know all of this stuff, feel free to say that as well. You can say it in the chat too if you don't want to.
I'll try to speed up if it's slow.
Yeah.
I'll just cover RLC super fast here. Hopefully, I'm guessing most of you have heard of it, and ask questions if I'm too slow. So if you have a resistor in a circuit, this is too big, brushes. If you have a resistor in a circuit, we can describe the series resistance of two resistors as the sum of the two resistors. So the total resistance here is the sum, we call it R3. And this can be drawn as a single resistor. Now, if you have resistors in parallel,
that's where you get Bucky.
1 over 1 over plus 1 over.
Yeah, definitely. This is terrible. So if we have resistors in parallel, we'll do 1 over like this. And this will be R3 equals 1 over R1 plus 1 over R2, and invert that. And so two 10K resistors in parallel will give us, oh, that's not right. Oh, that's why it's not connected. Should give us 2 milliamps because it's 5K, right? So an inductor, cover inductors next, is essentially an AC resistor. So in DC, with DC current flow, there will be no decrease in current for an ideal inductor in the DC current or DC circuit. So you'll see that the same current flows through here. So 1 milliamp or 1,000 microamps. If you have an AC source, the inductor will act as sort of an AC resistor. We'll get back to that at some point. It's not super critical. And then a capacitor will simply charge and then become a DC block. So where we use capacitors most in circuits are when we either are trying to block DC or when we are trying to filter AC. So you'll see in this DC current, DC source, we have no current flowing. However, if we add an AC source, see if we can run this on stop. Does not want to do that. Oh, yeah, that's why. Normally, a real capacitor will have some sort of series resistance. So if you use a real capacitor, you won't need a resistor with an AC source. Current will still flow, and it will not be infinite. Let's call it 1K on stop. So if we look at view and scope, you can see that in a circuit, in an AC current source circuit with a capacitor, which is essentially just a current storage device storing energy in the electric field, you'll see that the current is 90 degrees in phase behind the voltage. So you can use capacitors to create a phase shift in an AC circuit. All right. Capacitors, however, don't act like resistors and inductors in series and in parallel. So if we have two capacitors in series, our total capacitance will be double that of our all right, it doesn't want to run. That's great. Our capacitance will be double that in parallel, whereas in series, our capacitance will be half that. So it's the same equation for resistors in parallel, however, for capacitors in series. So we can move on to sort of the next topic, which is diodes. I'm definitely skipping over a lot of things. This is not the most descriptive description of capacitors, resistors, and inductors, but it's easier to see what they're doing in a circuit where they're actually doing something. So fortunately, this simulator doesn't let me show you frequency responses. So filters we can discuss when we do RF. In RF, we use generally LC filters, and for reasons that we don't have to get into now, we can move on to diodes. So an ideal diode basically prevents current from flowing in one direction. So we'll see if we have some circuit with a resistance and a diode. See that when we connect the DC voltage to the diode, with the positive going into the anode, so this is the anode, and this is the cathode of the diode, we'll see that current actually will flow. However, if we take this out and flip it around so that our everything is reversed, you'll see the diode stops the flow of current. Now, an ideal diode, that will always be the case. However, in reality, most diodes have a breakdown voltage. So if you apply a voltage greater than a certain diode's breakdown voltage, which we can use as then current will actually begin to flow in the opposite direction. You can use this in a controlled way, and they actually make diodes to do this on purpose. They're called Zener Diodes, and that reverse current flow, so basically the voltage overcoming the breakdown voltage of the diode, is actually a useful property. So you can use them as clamps, over voltage clamps. It's one of the most common ones. The second one is, that's the only one I can think of at the moment.
Ben, there's a question in the chat.
Yeah, definitely.
I'll say it. How are inductors resistors in AC current? Do resistors act differently in AC current?
Yes. So we can go back to that quickly. Let's discuss that. That's a good question. So if we take an AC voltage source, two-terminal AC voltage source, the easiest one to do this here, and we draw an inductor. Right. You'll see that, actually, this is a good circuit to do this in. So if we take this DC circuit and we look at the voltage on the resistor, so you'll see that, what the heck? So the voltage drop on the resistor is 9.5 volts. That's because there is a 0.6 volt drop over this diode. It's a Zener diode. And you'll see that there's a voltage drop across that. So essentially it's going to go from whatever voltage is on this side of the terminal to whatever voltage is on this side of the terminal from Kirchhoff's rule. Essentially says in a loop, in any loop in a circuit, the voltage drop around all of the components must equal 0. So in AC circuit, it's slightly different. So we'll have this inductor. Let's see if we can put view and scope. So you can see that, let's see here, what's this source voltage? 10 volts. Okay. So if we draw a inputs and sources, we go voltmeter and scope probe, put a voltmeter here, and a voltmeter here. And we'll try and plot both of those. Scope, view and scope. That's all right.
Yeah, that looks right, Ben.
Oh, wait, hold on. I'll put some labels. Okay, add voltmeter and scope probe. All right. So it's very weird. All right. This is not a great example, but in an AC circuit, maybe the frequency is not. It's a bad explanation. Anyways, in the AC circuit, at some frequency, the inductor is going to oppose the flow, or inductors oppose a change in current. So if you have an AC circuit, the current is constantly changing. So you're going to dissipate power through your inductor rather than your resistor. So I guess a filter would be a better way to describe this, but can't really explain those too well without a Bode plot. So we'll revisit that. Hopefully that answered your question. So we'll go back to...
Yeah, that helped. Thank you.
All right, yeah, no worries. So we'll go back to the diode. So in an AC circuit, diodes are very useful, especially in any wall outlet that you have in your house. So in every wall outlet that you have in your house, it's generally like any one of these, I'm gonna unplug my light, but this wall wart, doesn't show it, converts the AC power from your outlet into DC power for whatever device you're using. And generally, that will always use a diode. And that diode is called a rectifying diode. Essentially, it's going to limit the flow of current to only one direction. So we take and remove these scopes. And we put a scope on this resistor. You'll see that let's also put a scope on the AC voltage source. So you see that the AC voltage source goes all the way to the bottom and all the way to the top, whereas with your across your resistor, which is forcing the current to go through the diode, you'll see that you only get the top half, and that's because current can only flow when the polarity, when it's permitted by the diode, essentially. So this is a half, I think it's half bridge rectifier.
Yep, that's right.
Yeah, and so you can essentially only get half of the power transmitted because you only have half of the sine wave going through your resistor. So the solution to this is essentially to make a full bridge rectifier, which we can do with 4 diodes. Essentially what this does, this is why I like this online simulator so much. We draw another AC voltage source. Terminal. And we wire that up to our diodes. Ground to this side. And then we go and add a resistor here. We need some sort of load in order to make current flow. And take a look at view and scope. Something is not right. What do I do? Okay. Oh, maybe I need, oh, I know what I need. That's why. I need a transformer. So this is essentially going to allow the current to flow in a loop, which is what we need. Draw another AC voltage source. Here. And we'll see that on our output.
No,
This is not, something's not working here. scope. All right. Outputs and labels.
Yeah, this is kind of odd. I don't-
Scope. Ah, that's one. Okay. Yeah.
Oh.
Now we have a fully rectified AC voltage. So you can see both halves of the sine wave are in fact producing a positive voltage on the output. So you can see how current flows in this system. So we always have, let's switch it up to what your wall actually outputs. So it's going to be 150 volts, 60 hertz. And you'll see it's switching from one diode to the other as it allows current to flow as it's switching. So this is one of the, in our flight computers, this is one of the larger challenges we face, is dealing with ripple voltage. So we don't use AC voltage. However, we use switching regulators. I won't get into those, but essentially the way switching regulator works is it switches on and off the voltage, essentially a pulse width modulation. And so we need to smooth out this spiky plot of voltage here. So we need to store, go ahead.
Yeah, no, let's ask if anybody has an idea of what you would use
Ew.
there. So the reason why you use, so Quinn, just answering your question real quick. So the reason why you use a rectifier is because like the power from the wall is AC. So the power that you have from the wall is AC current. So this allows you to convert that to DC, which is used for pretty much everything else. But yeah, so what I'm going to ask is, anybody have an idea what component you use to smooth out that current?
Inductor?
You
No.
can use, go ahead.
Could
You can use an inductor.
Okay.
However, in this case, we have, don't know exactly how to describe it, but our, can I put a, let's see if we can do this. Add outputs and labels, add ammeter. Let me do this.
Ammeter has to be in series.
Yeah. Draw. Put some labels, ammeter. Okay. Can I add? Something's not connected. Oh, that's why. Ah, there we go. Wasn't properly connected. So if we look at the ammeter, I want to show the ammeter and the voltmeter on the same plot. But
If you delete the other ones, you can go to scopes, and I think like,
scope, remove scope.
and then go to scopes at the top,
draw
and you can
scopes,
go to
combine them.
stack.
Oh,
Yeah, or no, you don't want to uncombine.
and scope. Okay, draw, scopes, stack all.
Yeah.
Okay. So yeah, so our current is in phase with our voltage.
In phase.
Actually makes a lot of sense.
The peaks of the sine wave are at the same time.
Yeah, this doesn't explain why we would use a capacitor. But I'll just show you. In fact, you should draw a. I sent you the link for the circuit simulator. So you should all draw a full bridge rectifier like this. So to get a diode, it's just D, and then you draw. To get a resistor, it's just R, and then you draw. Transformer is Shift T.
You can just do the AC source, I think.
I think you need. So you need this loop here, right?
Oh, okay.
This
I
is
thought
why
it just worked with the AC source.
it actually does work.
It does.
Yeah.
Okay.
All right. Normally, you use a transformer, because you want to isolate the wall power from your circuit. So we'll do that again. Shift T. So the simplest way, in fact, with most outlets you'll use, we can just add an inductor in between our load and our source. So if we draw an inductor, draw a resistor, wire these up, we'll see that, this is why you don't want to use an inductor. All right, so remember how I said inductors were AC resistors, right? So on the output of a circuit with an inductor, might need to change the inductance here. Make it a millihenry.
Well, that just made it, because it's saturated now, because you're at 100 volts.
Scopes. Maybe I need more inductance. AC source, outputs and components, voltmeter and scope probe.
Scott, you can walk.
Scope. Okay, so that is working. Oh, I see. I was looking at after the resistor. Yeah, so that's 0 volts. Okay, yeah. So we don't have enough. Basically right now we don't have enough inductance to do anything. However, if we increase the inductance. So we go to, let's see, slowly increase it. Millihenries.
No, you got to go, because it's saturated 1.
Yeah. All right. So you'll see when we actually get the inductor starting to smooth out the output current, our output voltage actually decreases here. And we don't want that. We will still want our full power being transmitted, essentially, or our full voltage. So what we can do, so if we're going to keep doing the increasing the inductance, you'll see we get even closer to that smooth line. Go to 10. Keep going there. And 12.
Is 10 Henry a lot? I don't have a reference for
10 henries is a lot of inductance. It's actually, it would be an enormous inductor. So
let's see.
I guess if you want to find a photo, Tyler. Yeah, I guess I should mention this. So I didn't discuss the units. Skipping a lot of things. So a resistor has the units ohms, and you can basically get any size resistance in any package. So the regular, see if I can pull, I've got all of your kits for the Arduinos here, all of the components. So if I were to take one of these resistors out, you can basically get any size resistance up to like 10 mega ohms in a tiny little package. With a capacitor and inductor, they're both energy storage devices. So the size of the capacitor and inductor directly influences how much inductance and capacitance you actually have. So a typical capacitor size that you'll actually use in anything that we work on, really, it's going to be about 1 microfarad. So that's 1/1,000,000th of a farad. The farad is sort of the base unit for capacitance. Now,
if you've ever heard of like supercapacitors or railguns, those usually use capacitors on the orders of like 10 or plus farads, just to put it in perspective.
And so along with the capacitance, the voltage, if let's say you're using a higher voltage, the size of the capacitor must be larger as well. And this is because the larger the capacitor, or the higher the voltage you go, the less capacitance a capacitor will actually have. So closer to the voltage limit of a capacitor, the less capacitance your capacitor will have. I forget why exactly that is, but essentially you can't use a tiny little capacitor for a huge voltage. You have to increase the size. So if you look at like a 1,000-volt capacitor, that's 1 microfarad, it'll be huge compared to a 10-volt 1 microfarad capacitor.
Because the way it's about the way capacitors work, which I think you'll learn in physics too if you haven't already.
Yeah.
But the higher your voltage, it means you have to have essentially a bigger gap inside of the capacitor to not short it. Which you will see if you've ever heard of a capacitor making magic smoke. That's a capacitor shorting, and
Yep.
you probably all will see one at one point working
And
on
you don't want
electronics.
that. Yeah. So I guess, and all the way back to inductors. Inductors store energy in their magnetic field. So the larger the inductor, essentially the larger magnetic field it can establish and the more energy it can store. So I don't have a board here, but the inductors I use on a regular basis are either microhenries or nanohenries. So either 1 millionth or like 1/100 millionth of or 1 billionth.
Yep, and that's the exact
Henry.
problem we're working on.
Yeah. So this would be an absolutely ridiculous inductor to get any sort of current smoothing. So what we use here is actually just a very large capacitor. And this is not difficult to get a 100 microfarad capacitor. Is this going to do this? Oh, it's not connected. Yay. Delete wire.
Okay, I think we found the one problem with this circuit
Yeah,
software.
there we go. All right. It's a little better. Oh, what is it doing now? Oh, that's not connected. That's why. There we go. What is it doing? Anybody tell me what it's doing? Oh, I see. Let's see. Let's do this. This needs to go to ground. And this can go wire.
Your graph will update once it gets off the end of the thing.
Scope. View and scope. Ah, there we go. All right. So now you can see with the capacitor doing our filtering, our output voltage is still pretty close to our input voltage of 115 volts. And our ripple is significantly decreased. So generally, instead of putting one huge capacitor, we go back to that, what I was discussing before, and we'll use multiple smaller capacitors. So this is the advantage of that property of capacitors. So on any sort of power supply, you'll generally see just large rows of capacitors. And that's because
it's cheaper.
Yeah, exactly. And takes up, doesn't always take up less space, but can. Doing capacitor loop with no resistance. Yeah, these are not, I was thinking these are ideal capacitors. So we might have to add resistors in between all of these. Well, anyways, I guess we can just skip that and demonstrate that by increasing the capacitance even further.
Emma, those are connections to ground. So
Yeah.
whenever you need something to like, you always have like a common ground in your circuits usually.
Yeah.
And that, especially when you're dealing with AC current, you have to have that to make sure you're not.
Yeah. Well, so in this case, you don't actually need a ground. It just simplifies drawing things to tie this end of these diodes to ground. However, if I delete those grounds and draw these wires here, increase this to 1,000 microfarads, and view and scope. So you'll see now we have our ground. And our output voltage with 1,000 microfarads, or 1 millifarad, gives us a very smooth output voltage with very close to the input voltage.
Ben, can you pull up the picture of the Arduino board real quick? I just want to show them one of the capacitors we have on there.
This is in intro, yeah, we can do that. Intro Avionics. Oh, I'm already here. Original. All right, yeah. So these are these capacitors here are 4.7 microfarads, and these are aluminum electrolytic capacitors. So they're different types of capacitors, and that's a different, I can send you something if you're curious about the differences, but they actually are very different and are used for very different things. These ones here, these yellow ones, are ceramic-based capacitors, and these are either 1 microfarad or 0.1 microfarad. So you'll have your hands. Oh,
I
go
think
ahead.
we also have some picofarad ones on there too.
Yes, actually, these ones are, so this one is probably 0.1 or 1, and this one's probably 0.1 or 1. These two are 22 picofarad, and essentially they are loading our oscillator. And essentially to load the oscillator is going to bounce back and forth. In order to get it to oscillate at the right frequency and give us the right output voltage, we essentially switch the sides, fill up a capacitor, and do the same, switch sides, fill up the capacitor. And that voltage is what essentially comes back and is delivered to our microprocessor here. So we can discuss that a bit more next week when we actually assemble these, assuming we have everything. I'm really hoping we do. But,
Yeah.
Yeah. All right.
Yeah.
So are there any questions about sort of the basics of diodes, resistors, inductors, capacitors? We can quickly discuss. Yes.
So resistors, capacitors, they work the same. They work the same as they would in AC and DC.
Resistors and capacitors?
Yeah.
Not well. A resistor, yes. A resistor is just always going to dissipate power. That's its job. So a resistor, you can describe the power dissipated. It's the P equals VI, so the voltage drop across the resistor times the current in the resistor. That'll give you the voltage, the power dissipated in watts. In a AC circuit, capacitors do. Capacitors are never used in DC circuits.
You mean
Unless they're-
AC?
Say again?
Capacitors aren't used in DC circuits? They're used in DC circuits.
No, almost rarely they're used in DC circuits.
Oh.
Actually, almost never used in DC circuits because in a ideal DC circuit, there's no ripple, there's no change in voltage, right? So the reason why we use capacitors in DC circuits and integrated circuit-based designs is to essentially, most common is to decrease the presence of AC voltage, which can mess up our internal circuitry of our integrated circuits, so our processors. We call those bypass or decoupling capacitors. I will discuss those with the Arduino. And otherwise, you can use them as just energy storage devices. So you'll see people use them like batteries in cars. That's the only other way you would use it in the DC circuit. But yeah, capacitors are almost exclusively used when AC is involved at some level. But yeah, I would be glad to send you or explain a bit more about those at some point. Just don't want to get into like the physics 2 descriptions of them.
Yeah. Fair enough. Yeah. Okay.
I have a question.
Yeah, definitely.
So in between like the square of the diodes
Yeah.
and the energy source, is that a transformer?
Right here? Yeah, it's a
Yeah.
transformer.
What does that do exactly?
So a transformer is, the easiest way to describe it is it's two inductors connected by a common core. So that core is basically a wire for a magnetic field. So what a transformer allows you to do is electrically isolate two circuits. So we have a Let me see if I can draw out some paint. This is a mess. I can't believe I did this file. New. Don't save. All right. So if we have a transformer, we will have a common core. So a lot of times they'll look like this. There's a lot of ways they do them. And then we'll have wraps of wire around this. And so, Tyler, do you remember the name of the law that basically states that current flowing or a change in current results in a change in magnetic field? I forget, it might be like BOSOR or something like that. Anyways, so in an AC...
Faraday's law of induction.
Yeah. So when you have current flowing through this inductor, like if you were to cover one side, it would just look like an inductor and cut this off. You're going to create a magnetic field in this core. And so you'll actually have basically a flow of magnetism. It's the best way I can describe it. And actually is very similar to electronic circuits. You can make magnetic circuits. A flow this way. And this will induce a current in your wire winding on the other side of the transformer. So let's say you go this way, follow the right-hand rule, you will get a magnetic field. Let's draw this the other way. You'll have a magnetic field going this way, and this will go in here, and the magnetic field going upwards will create an electric field in the windings that will go, I'm trying to figure out which way I drew this. Well, let's say it goes this way. And so you can electrically isolate these two circuits with basically two windings and a big chunk of metal. And this core can change materials and change the properties of the transformer. You can also use transformers as a way to change the voltage of an AC source. It works very similarly. Perhaps that's not, I wouldn't say a resistor divider is similar, but let's say you have 10 windings on this side. No, it's not. If you have 10 windings in your transformer on this side, and you have 5 windings on this side, and you have 120 volts in, you will get, correct me if I'm wrong, 60 volts out, right? However, if this is 1 amp here, 1 amp going in, you'll get 2 amps out, because essentially you have to conserve power. So that was a long-winded explanation that a transformer isolates two AC circuits, electrically isolates them, that is. All right, that answer your question?
Yeah.
Any
Okay.
others? Yeah.
Let's. Oh, do you want to do one more thing before we? I want to give them something to do at some point.
Yeah, definitely. Okay.
Do you want to do one more thing, or what do you think?
Yeah, I'll try to explain. Actually, I want to hear. Would someone like to explain how a transistor works? Is there anyone here that thinks they know really well what a transistor is and sort of how it works? Okay. Yeah, I thought so. So maybe you guys have come across this explanation of a transistor before, but back in Bell Labs in the 1940s, they were trying to create a device that would be a 3-terminal device, and they could vary the output voltage. Oh, someone said something. Doping processes. Yeah, so we won't get into the doping processes, but that's essentially how they work at the sort of molecular and atomic level. But at sort of the higher level, back at Bell Labs, they wanted to create this mystical 3-terminal device. I forget the original name for it, but they somehow settled on transforming resistor, because essentially that's all that a transistor is. If you combine the prefix and the suffix, it is a transforming resistor. It's just another resistor that you can control with that 3rd terminal. So I think transistors get overcomplicated. They say, oh, it's a switch, oh, it's an amplifier. That's really just a resistor. And so the easiest way to show you this is with a resistor divider. So if we have a DC voltage source here, can anybody tell me if this is 10 volts, what is going to be the voltage between these 2 points? These are 1K resistor, and a 10 volt supply. Does anybody know? I'm getting messages, chat.
5 volts from Johnny and Ethan.
Yeah, it's 5 volts, right? And that's the via Ohm's law. Yeah, exactly. So this is 10 volts, 2K. Well, not necessarily via Ohm's law, is it? It would be via Kirchhoff's rules, right? Because we have 10 volts, these are equal resistance, so we have to drop equal amounts of voltage over each resistor, right? So it would be 5 and 5. So this is the premise of the voltage divider, which essentially says that we have to that we can basically create an output voltage here based on the value of these 2 resistors. So the output voltage here is going to be 6 volts down at the bottom. And you can change this, and you can do 4 volts or whatever else it is, and we get, oh yeah, that's why 4K. And we get over here 8 volts. So seeing that, oh, do that. Anybody tell me? Oh, that's text. Draw. Active components. Transistor, bipolar, NPN. Oh. Draw. Active components. Transistor, bipolar, NPN. All right. Knowing that a transistor is really just a transforming resistor, anybody tell me what this looks like? If what we saw previously was a voltage divider. This is also just a voltage divider. So that's the easiest way to see what a transistor is. And so if we take the transistor and we give it some voltage on the input, which is called the base, we get some output. Draw inputs and sources, voltage source. All right. And so this needs to be probably higher. Well, maybe it's going to fall apart. Let's see. Oh, this is what I need. Well, Well, essentially what I was trying to get at here was that we have an amplifier using 2 voltage dividers. We can essentially change the resistance of our transistor and get an output voltage greater than our input voltage based on some higher input voltage. Let's see if we can just do this quickly. Probably not. Let's make this 10 volts. Okay. We're going to draw a inputs and sources AC voltage source. Wire here. Wire here. Wire. Oh. Draw a voltmeter scope probe, and then mess with these resistors until it works. Want this to be I may not be able to get this working, but a little too ambitious. All right. Anyways, we'll come back to this. I don't want to distract you from other things at this point. However, the transistor is the basis of basically everything that we make, every piece of electronic equipment that you have nowadays. So I guess that's all I have. I don't know if you have anything else, Tyler. Probably not going to get this working.
Should I make this stuff? Okay. Yeah, I don't really know quite what.
I was trying to make basically this a type 1 amplifier, and it functions off the principle that a transistor is just a resistor, and you can change the output voltage of the transistor.
Okay.
So that's all I have. Potentially I can get this working, but until then, I suppose we should move on to Eagle/Linux.
Yeah, well, I was thinking we should have everybody just to like do it themselves on this software, just so that they can see. I'd say like one of the rectifiers we did with the diodes would be pretty cool. Something that should be fairly straightforward, just to like see themselves. Like that's what I want to do. I want you guys to see for yourself, like the same thing that Ben showed you, but just like make it yourself with a circuit, or even you could do something similar. Like you could do a half-wave rectifier is the one that the first one that he did. If you want to design that, but yeah, if everyone wants to try that, and then I don't know, like send a screenshot, ask questions, just figure out how like the different electronics components go together. What's the website again, Ben?
I think I sent it. Let me send it again.
Yeah. Solstad?
Yep. No.
Yeah. Sorry, this week was a little slow, guys. Well, this will be a lot more exciting when we're back on the actual pace that we had planned for. Assembling the boards will be pretty fun, from what I can tell.
Should we get a soldering iron, or how is that?
So
gonna
we
work?
have soldering irons for everybody. Well, except for the 3 people that I have. So we have 22 people. There's 3. I have 20 soldering irons, and I had 3 people. That's why I had the question on the thing asking if you had a soldering iron. So I do have enough people. Like, we have enough soldering irons because a couple of people have their own. Yeah, so that's good. We'll send you soldering irons. And then we're also going to send some safety equipment with that, assuming that it gets through res mail.
Cool.
Yep. Yeah, because the safety goggles are currently in res mail and not actually there, which is kind of annoying.
COE sent all the incoming freshmen safety goggles over the summer.
That
Oh,
is
cool.
good to know.
Yeah, wait.
That is very good to know.
Fine. They're like these ones. I don't know if it makes a difference.
Huh. Yeah, those are the same ones we have in the labs.
Yeah.
Yeah, so
Yeah.
we're going to have a pickup on campus
Okay.
next week sometime for people who are around here. Just answering the question from chat.
Yeah, if they don't make it through res mail.
Good to know. Good to know. But yeah. Also, I mean, if we need to, we could just go to the store and buy some safety goggles at
Yeah.
what? True Value? Yeah, True Value has them.
I tried to make my circuit, but the graph of current is really weird.
Can I let everybody share their screen? I think I can.
Yeah.
Yeah, you can allow participants.
All
right?
participants. There we go. Yeah, if you want to, so if someone wants to share their screen and show their circuit, feel free. It's only one at a time, so. Yep, I'm gonna go first.
I don't know what my current's doing.
Can't see.
Huh.
All right, it's not just me.
It's very odd. Wait, where are you measuring your current?
I have no idea. Where should
Yeah, how to remove that scope.
Yeah.
And
So right
so
click
right-
on the scope at the bottom. Yep.
and
and
then
then
right
click
click
on
on
the
the resistor.
resistor. Yep.
View and scope.
Huh?
There we go.
Yeah, that looks right. More right. It's still doing something weird, but so if you make your capacitor 1,000 instead of 10,
All right.
we should see.
Oh, there.
There you go.
Yeah.
I can stop.
Yeah. So you were probably looking at the current on one of the diodes or one of the wires around there. Diodes tend to do very weird things.
What else did they send all of the freshman engineering students?
Just the safety goggles, pretty much.
Because they make you buy the Spark Fun kits.
Yeah.
Huh. Interesting. But yeah, Spark Fun kits are pretty awesome. I should have just when I bought mine, I felt kind of dumb because I'm like, I should have just put this together myself. It would have been cheaper, but I didn't want to risk it. But yeah. Okay. Yeah,
Do we use them a lot, the SparkFun kits?
You use them a lot in
D1501?
Cornerstone. Yeah, so 1501 and 1502, you'll use them a ton. After that, apparently the Mechie classes are using them now, like, because they're doing remote labs, so they're using the red boards, like, for the lab, which I am surprised about, but
Yeah.
Most classes just ship you what you need for labs, or do it all digitally, which sucks. But like my electronics lab right now is completely digital, so everything's in software, and yeah, it sucks.
Yeah, that does kind of.
I haven't actually done it yet. But yeah, anyone else want to show their circuit or is having problems with it?
I think you got the layout, but I don't know why it's not like